All right, so today we're going to go through two more tutorials. So just recap, what is momentum equation? So momentum equation give you uh, the third equation that you see on the screen here. So when you take momentum divided by time, you get force. Yeah. So what is the momentum fundamental? Again, you should able to explain from the beginning. So momentum equal to mass time velocity. So if you want to define momentum for the force, you call out the second Newton law, F equal to ma, and acceleration is velocity divided by time. The product of mass time velocity, you get momentum. So when you take momentum divided by time, you get force. So when we use the momentum equation, actually we're looking at force inside the system, and then we build the integration relationship for the control volume and control surface. Let's look at the tutorial question for today. Okay. So today we look at your handout question 21. So let's say you are having a water dam or water tank, if you like, and you let the water flow from the left to right. So if you open the gate, the water gate, the water will flow from left to right, and the velocity will move at point number 1 here. Velocity is 1 meter per second. The height of the water is 3 meter. So in this case, we put D1. D refer to your Y or your H. And for point 2, the velocity is 7 meter per second. The height of the water here is 0.4 meter. All right. So we need to compare the horizontal force of the water at the gate when the gate is closed and when it's open. So we have two scenarios we need to consider. What happens if we close the gate? What is the force feel by the gate here? And when it open, what is the force at this region? So if you stand here, what is the force that you feel when the door is open? So what happened if you close the gate? What happened? So because we are looking at a momentum equation, we deal with the velocity of the mass, right? Mass moving at a certain speed, it create momentum. So it will we need two set of calculation for this scenario. One is for closed, one is for open, and the flow we assume is steady. And also we assume we have a compressible flow. Yeah, and we have a hydrostatic pressure in this case. All right. Now, before we start, we need to start with the control volume. You need to know how to draw control volume. So control volume is quite strict. In this case, you copy the shape of the system, and then you draw the dashed line like what you see on the screen here. Yeah. So you set what you need to focus on. And in exam, be careful. If you draw a straight rectangular in this area, you get the wrong control volume. So you have to go down and then go up again. We only consider the space traveled by the water without the device here. Okay. The first step in solving momentum equation is to set up the control volume, like what you see on the screen here. And it depends on the system that we're looking at. In this case, we're looking at dam, so we draw the system, the control volume. After you draw the control volume, you convert your control volume into a free body diagram. What I mean by free body diagram? Meaning only forces is seen in the free body diagram. So we know that once we have a medium with a mass, then gravitational force going to act on it. So we know that force consists of two components. We have a body force and surface force. So body force is deal with gravitational force acting on a mass. Surface force is what happened to the surface. Yeah. So in this case, we have W. In this case, we have water, and then as the water flow, there's a friction force of the water when it contact with when the water contact with the surface bottom. And then we have pressure on the left. So we know that as we go deeper into the water, the higher the pressure. So that's why the distribution of your pressure on the left hand side is a triangular shape. It's not a rectangular. Yeah. So remember when you draw the profile of the pressure for hydrostatic pressure, you not always have this shape. You not always have a well-distributed underwater. You need to draw this triangular shape of distributed pressure, because as you go deeper, pressure increase. Yeah, as you go deeper, pressure increase. So we have a triangular shape here. We talk about hydrostatic pressure here. Yeah, so it will apply the same for the right hand side. We have a small triangle over here. However, the direction is going into the control volume. So one is on the left, the pressure is acting from the left to right. On the right hand side, bottom corner here, you'll see that the arrow is pointing to the left. Yeah, pointing to the left here. And we need to find the two forces inside the system. One is in x direction, we label as Rx. One direction is in the y direction, we label as Ry. So you need to know how to convert the complete system into something into control volume. Then after that, you add in forces to become a free body diagram. So there's a standard steps for that. Yeah. Okay. So these are the explanation for all the marking that you see on the screen here. Okay. I repeat that. Okay, we have assumption. Yeah, so we have a few assumption. We ignore the friction at the ground there. And then we don't have body force in x direction in this case, because body force always in y direction pointing down. So if we look at x direction, body force we can cancel. We have a steady flow. So again, when we have a steady flow, you can cancel something in the continuity equation and also momentum equation. Compressibility flow, uniform flow, and so on. So we pull out the momentum equation. Momentum equation is quite direct. So you know that on the left hand side is on a force. Force, you have two components, body force and surface force. On the right hand side, you have integration component. One, you focus on control volume. One, you focus on control surface. So when you look at x component, you rewrite the governing equation. You rewrite the momentum equation above. In this step is that we cancel out the term that we apply the assumption just now. Meaning in x component, we don't have body force in x component. And we have a steady flow, so we cancel the first term over here. So we arrive at a very simple equation where we have surface force in x direction will be equal to integration of your u of your v rho v dot dA. So in this case, you should know how to draw the magnitude for all the control volume here. One is on the left, one is on the right. So you have 0.1 and 0.2 here. So you should know how to draw the area and the velocity vector. So we are looking at x component. So you switch the v into small u to show that you understand that you are looking at X component. The next one, you just pull out or make full use of your free body diagram. So what is the component for your force for the left-hand side? Is your Rx plus what is on the left and what is on the right. So this pressure, hydrostatic pressure on the left, you need to convert into forces. All right. So again, you know that pressure equal to force divided by area. So you want to convert this pressure into force. You take pressure times the area of this region. All right, area over here. Then same with this one. Yeah, same with this one. So FR1 means reaction force at on the left hand side, 0.1 here. FR2 is the reaction force at point number 2 here. Rx is reaction force at the gate here. And for the right hand side of your integration component, you have 2 points there, so that's why you have a 2 integration. Yeah, so you have integration of your area 1 plus integration of your area 2. So this, the first one will arrive this one, the second one will arrive this one. So for the first one, you should know why you get a negative. For the second one, why you have a positive there. Okay, just to recap. So for your convenience, I draw it for you. So for 0.1, control volume, 0.1, area always pointing out. However, the velocity is flowing from the left to right. So the products of these two, you get negative sign. For control volume point number 2, you draw the area always pointing out. You look at the velocity move to the left to right. So this is velocity. The products of V2 dot area will give you positive sign here. Then after that, okay, the A, why suddenly you see WD1? W is the width of the structure. Yeah, the width of the structure. This is your W. This is your Y, or in this case, given as D1. So same with here. So you want to find the area. So you take your width times the height of the water. So you take WD1. Same with the second one on the second side here. So you have U2 rho V2 WD2 in this case. All right. Then the next one is to find what is the reaction force for your hydrostatic pressure on the left. So FR1 equal to integration of, you take P1 times the area of section 1 here. So you integrate with D1, with the height of the water. So you change your dA into dy times W. Yeah, your dA is W dy. So you rewrite the equation. So 0 d1, again d1 here is not diameter, it's the height of the water. P1 dA, you can write as integration of d1 P1 W dy. So you know that pressure, when it becomes hydrostatic pressure, you can use rho GH, hydrostatic pressure. So the H here is D or your Y. Yeah? In this case, we use Y. So you change the formula from pressure into rho GY, and then you pull your width outside there. Pull your width outside there of the equation there. You do the integration procedure, you will get W rho G. You integrate Y you get y squared divided by 2. Substitute d1 inside there, you arrive at w rho g d squared divided by 2, and this one refers to the left-hand side of the hydrostatic pressure. The reaction force on the left-hand side, R1. You do the same for number 2 here. You'll get this equation. You integrate the pressure times the A, and you write y dy and w. Yeah. So again, in exam, it's important to show the steps here. There's a mark for the steps. Yeah. And you do the integration procedure. Again, you arrive at w rho g y squared divided by 2, and you substitute d2 inside there, you'll get w rho g d2 squared divided by 2. So from here, you get what is your R1 and what is your R2. Okay, then you can find the answer already. Okay. So you rearrange the equation. You will get w rho g d square plus d1 square and d2 square plus rx. There is, I think there is a mistake here. This one is typo error. It should be negative because if you move, R2, hold on. Yeah, R2. FR2 is to the left hand side. FR2 is to the left. So we assume all the positive direction is positive to the left. So when you put the answer inside this equation, your FR2 will be give you a negative sign in the formula. Yeah. So there's a typo error over here. So there's a negative sign for your FR2 component. Then you simplify it, you'll get this form. And then you further analyze, to analyze. Just now the step is only covered on this side. We haven't looked at this side. Yeah. So on the left hand side, you arrive at this equation. On left hand side. The next slide will show you what is the products of on the left hand side component here. So you substitute what you get so far, left hand side, and then you copy the right hand side formula down. You get this form. Then after that, you substitute, you look at the diagram, and then you substitute what is the U1 at station 1 or point 1, you'll get equal to V1. What is V2? V2 here is U2 here is V2. So when you substitute in, you'll get V1 square and V2 square in the next steps. So in the next step, you will get W rho G divided by 2 D1 square minus D2 square plus Rx and negative rho V1 square W D1 plus U2 rho V2 square W D2. So you will have this equation. So far, there's no complex concept here. It's just a rearrangement of the mathematics equation. And then you put your Rx in on the left, and then you move all the equation to the right. Okay. So just a side note, what means by the first term and second term? The first term is when the value is valid when the gate is open. And the back one is the hydrostatic force on the gate here. Yeah. So again, This is just for extra information. Yeah, for extra information. It's important that you know how to arrive at this equation. Then after that, we'll compute in terms of force per unit width, because the width is not given. The width is not given, you're not able to calculate. You're not able to complete this calculation. So we rearrange the mathematics equation, like what you see on the screen here. We factor out all the W, and then we move to the left. We get Rx divided by the width equal to this term minus this term. The rest is a substitution of value. You will get this one, yeah. So in exam, you need to show what value you use in the steps, and then at the end, you arrive at 18 minus 43.2. You will get Rx over W equal minus 25.2 kilonewton over meter. So this is your Rx direction. So your Rx value is negative 25.2 kilonewton over meter. It means that you have a negative sign, means that in reality, the direction is to the left, yeah? But if you want to use back the free body diagram in this direction, make sure you carry the negative sign together, yeah? So always orientate your answer in the general axis, X and Y, positive in this direction, yeah? So this value, if you put negative throughout the answer, it will help you to secure a correct answer, yeah. Because sometimes if you flip the direction already, you put in positive, but you forget that X is positive to the right, then you'll get the positive negative sign wrongly. Okay. So again, what is Rx? Rx is the external force acting on the control volume applied to the control volume by the gate. So we need to flip this Rx to K. Yeah. Force on the water is K. So you need to flip Kx equal to negative Rx. So if you have a gate like that, yeah. If you have a gate like that, to counterbalance the Rx, there is a Kx. There's a Kx component to counterbalance the Rx. The force of the water on the gate is Kx equal to negative Rx, is the opposite direction of the Rx here. So you just flip the signs from positive to negative. So the force of water on gate, the answer is 25.2 kilonewton over meter. So you need to differentiate what is the external force, what is the force on water, force on gate, force on gate. One is force on a gate, one is force on the control volume. So the Rx here is you build based on your control volume. So the Rx direction is referring to the control volume, external force acting on the control volume. And if you want to look at the force acting on the gate, it is the opposite direction of the Rx. So that's why you put a negative Rx here. All right, we flip the direction of 25.2. This is the first scenario. So what happens if we have a closed gate scenario? Just now it's an open gate, because we assume it's an open gate here. Yeah, we assume the first scenario, this equation, when you open the gate, the force on the gate here will be 25.2 kilonewton over meter. What happens if you have a closed gate? So when you close the gate, there's no flow in this section. There's no flow. When there's no flow, there's no height for D2. Your D2 will be 0. Yeah. When you close the gate, your D2 will be 0. So again, you substitute back the numbers, you will get the Rx will be negative 44.1 kilonewton. And again, we are interested in the load, the water load on the gate. So you flip the negative sign again, you will get 44.1 kilonewton over meter. So what does these two numbers tell you? So it makes sense, right? It makes sense. So when you open the gate, the flow will flow without any the force acting on the gate will be less. So when you open the gate, you only have 25 kilonewton. But when you close the gate, it will go to 44 kilonewton. So if you close the gate, of course, you have more force rammed into the gate here. So you will have more hydrostatic pressure acting on the gate. So when you open the gate, so of course there will be less force acting on the gate here. Okay, so this is how you find the reaction force and the force water on the gate. Yeah. So we go for the second tutorial question. Do you guys need a break, or we just go ahead? Go ahead, huh?
No need. It's okay.
No need break, huh?
Yeah.
Okay.
Just continue.
Okay, just continue. Okay, we go for your tutorial question or handout number 22, which is the last question for this chapter. So we having a conveyor belt, and we have a hopper that dropped the sand onto the conveyor belt, and the velocity of the sand is 1.5 meter per second. The velocity of the belt is 0.9 meter per second. So the control volume is given in this case. So we have 0.1 and 0.2. So again, your 0.1 area is this one here. 0.2 area is this one here. So you need to be aware of the control volume area and velocity. So area, if you like that, area will be pointing out. Velocity will coming in. Again, the products of 0.1 of velocity, vector, and area will give you negative sign. In this case, control volume like that, area pointing out, area 2, velocity going out, v2, product of vector v and a at 0.2 will be positive. Okay. So okay, the sand fall vertically from hopper onto the belt, speed is given, flow rate is given. So flow rate is 225 kilogram per second. The density of the sand is given. And before the hopper is open, the conveyor belt is empty. And then the friction in the drive system roller here, you can ignore. We need to find the tension required to pull the belt while the conveyor is filling. So we need to find the force that able to move the sand. So we by having said that, we need to find the mass on the conveyor belt so that we can pull the conveyor belt with the correct tension. All right. So again, the control volume is given, so it's very convenient. And in this case, because we deal with the mass itself, so we need to pull out the continuity equation. All right. So the first equation, you're familiar with it. It is a momentum equation. The second equation on the screen here is continuity equation. All right. So you might have question when we need to use continuity equation. So you need to use continuity equation when there's a change of direction in the system. For example, this case, the the sand is coming in from point 1 in y direction and it going out in x direction. So you need to make sure that your system is balanced. Right, the system is balanced. You prove with the continuity equation. Okay. All right, we continue. So again, we have a few assumptions here. So the first assumption is our force in x direction will equal to our tension belt here. Tension of our belt. Our body force in x direction will be 0 because gravity always pointing to the y direction. So if you consider only x direction, body force you can cancel. We have a uniform flow in section 1 here, and all the sand on the belt will move with the velocity of the belt. When the sand drop here, it will move according to the velocity of the belt at 0.9 meter per second. So there are two speeds here. One is the sand from hopper, which is entering speed 1.5, and one speed is in the x direction, one is y direction, 1.5 is y direction. So it's good that you always convert the numbers into vector form. So for example, v sand, you can write v sand equal negative 1.5 j hat meter per second. Just to remind yourself that this component is going down in y direction, and the v belt will be equal to 1.9 because it's along x-axis, so it's positive I hat meter per second. I means for the x direction. Okay, so again, because of we're considering on x direction, we can cancel the body force. Yeah. So you rewrite the momentum equation in x direction. So Fx equal to surface force in x direction. You should be able to answer or explain why you can cancel out the body force. Yeah. Equal to momentum equation, one in the control volume, one in the control surface here. So in this case, we cannot cancel the control volume because we don't have a steady flow inside here. Yeah. We don't have because all the time is filling the sand. So we don't have what you call a steady system for the control volume here, because you keep adding the volume inside the control volume here. So you convert the V, capital V in x direction, you get U. Same with this one. And then we assume that our Fx equal to T belt, so we replace the T inside the equation on the left here. So T, then we continue to calculate. So for the control volume, we have this equation. For the control surface, you look at what is in, what is out. Again, I already draw the area vector and velocity vector just now. So the first one, you get negative sign. The second one, you get positive sign. Yeah? All right. Then you look at what is U1. You convert U1. U1, you look at the diagram. U1 is negative V sand. All right, V sand. And U2 is V belt. Right? U2 is your V belt. So U2 will be your V2. U1 will be negative V1. V1 is the sand. Huh? The next one is just substitution. Huh? The next one is just substitution. So for U1, we have no flow in section 2. Yeah. So our tension equation only reduce to integration of your CV U rho times the volume. Yeah. So our this component U1 is 0. U2, there's no flow over here, because if you look at diagram, there's no, not yet, there's no sand falling out. There's no sand flowing in section 2. So there's no flow. Yeah. So again, U1, section 1, why your U1 equal to 0? Because we're looking at x direction. This equation is a x direction. So what is the direction of your U1 here? It's y direction. So you don't have value for section 1 here. Your U1 here is moving in y direction. But this equation, you are focusing on x direction. So your U1 equals 0. Clear, Ku and Amir?
Yes, sir.
Okay, yeah.
Yes, sir.
Yeah. Okay, so you reduce to T equal to your control volume integration. Yeah, and then you just replace the velocity that you know. So in this case, your U equal to your belt lah. So you can pull your U outside, replace with the velocity of the belt. And the rest is just integration steps. So when you integrate rho dv, you get the mass of the system. Rho times velocity, rho times volume, you get mass of the system. Mass of the system. So, and then the tension of in the belt is the force required to increase the momentum inside the control volume here. This is just a side note lah. This is a side note about the tension. So the tension is increasing. Although your velocity of the mass in the control volume is constant, but the mass is keep adding from the hooper here. The mass is not constant. Although the speed of the belt is moving in the constant speed, but the mass on the belt is not. Yeah? So it means that if you look at the equation here, your VB is constant, but the mass is not. The mass over time is not. The change of mass over time is not. Yeah? So in this case, because your mass is changing, so you need to use the continuity equation to check what coming in from 1 must same with number 2. So we look at continuity equation. We're already done with the momentum equation. We arrive at this conclusion that we need the help of continuity equation to replace this term. Yeah, because we cannot continue to solve this question. We still have an unknown here. So we need one more equation that help us to solve the mass over T here. So what we need help is from the continuity equation. So continuity equation, again, we have control volume and control surface dimension. Rho dv plus rho v dot dA equals 0 because we have a continuity equation, principle. So we move your control volume, control surface term to the left, to the right here. We get a negative sign. You know that rho dv is a mass. Mass with the del dt is del of mass divided by t. This is what we want. We want to substitute what is this one in the momentum equation. So we get the help of continuity equation. We try to find what is del mass divided by del t. In this case, we know that del mass over del t equal to negative integration of rho v dot dA. This is from the continuity equation. So again, we know that rho v dot dA, you take rho times the velocity times area, you get mass flow rate. Again, how do you know you get mass flow rate. You use dimension to do analysis. Rho is kilogram over meter cube. Velocity is meter per second. Area is meter square. So you cancel meter times meter, meter cube divided by meter cube. The rest you only have kilogram over second. So kilogram over second is mass flow rate, m dot. Yeah. So it was given in the question that your mass flow rate is 225 kilogram per second. In the statement just now, the flow rate of 225 kilogram is given. So you just substitute from the continuity equation, your rho, your del m divided by del t equal to 225 kilogram per second, which is your m dot. Your m, the mass flow rate of the sand is 225 kilogram. You take this number, substitute in the momentum equation just now, you will get the answer for the question. So VB, your tension equal to VB times the m dot s, it is a mass flow rate. So you know what is your VB? VB is the velocity of the belt, 0.9 meter per second, times 225 kilogram per second. You need to convert in Newton, yeah, in Newton. So tension, the answer is 203.4 Newton. Okay, so again, one of the trick to do conversion is that you always remember call out what is the fundamental equation for force. You use second Newton law, F equal to ma. So what is the unit of mass is kilogram times acceleration is meter over second square. So it meaning that 1 Newton equal 1 kilogram meter per second square. So what you get here is kilogram meter per second square. So here you convert into, you know that when you get 1 kilogram meter per second square is equal to 1 Newton. So from there you directly convert, you convert into Newton. Okay. So with this, we end our chapter 3 lecture. So let me stop the recording.